Hello students, today in our class we are going to see the laws of motion, and the session for today is session number 6, and today we are going to see the topics of dynamics of circular motion, centripetal force, vehicle on a leveled circular road, then banking of tracks. First of all, let us see the dynamics of circular motion. Circular motion is one of the very common type of motion that we come across in our daily life. A particle can be in linear motion with or without any external force. But when circular motion occurs, there must be necessarily be some force acting on the object. In other words, without a force, circular motion cannot occur in nature. So in a circular motion, force can change the velocity of a particle in three different ways. First one, the magnitude of the velocity can be changed without changing the direction of the velocity. In this case, the particle will move in the same direction but with acceleration. Example, a particle falling down vertically, or a bike moving in a straight road with some acceleration. Then the direction of motion alone can be changed without changing the magnitude, that means the speed of the vehicle. If this happens continuously, then we call it as a uniform circular motion. The clock usually have its own uniform circular motion. See, in this picture, the acceleration is towards and opposite, and the bike have a negotiable space. It has a north and normal force here, and this is the force towards the ground, and this is the acceleration due to gravity. So the net moment above the CG is equal to 0. That means the center of gravity is equal to 0. It stops the bike from the falling down. Third one, both the direction and magnitude. Here the magnitude is meant for the speed of velocity can be changed. If this happens, non-circular motion occurs. See, a best example is oscillation of a swing of or a simple pendulum, elliptical motion of planets around the sun. Okay, these are the examples for this term. Today we are going to learn or deal with some uniform circular motion and non-circular motion. Centripetal force. If a particle is in uniform circular motion, there must be centripetal acceleration towards the center of the circle. If there is acceleration, then there must be some force acting on it with respect to an inertial frame. Already I explained you about this inertial frames, and this type of force is called centripetal force. That means a centripetal acceleration towards the center of the circle. Okay, now see, in this picture you can see all the forces are towards the center of the circle, even though they have their own directions, but it moves towards the center of the circle. So, according to Newton's second law, the centripetal force is given by FCP is equal to MA CP which is equal to mv square by r. Here Cp represents the centripetal force. Actually, the word centripetal means center seeking force, and in vector notation f dash Cp is equal to minus mv square r into r cap. In uniform circular motion, f vector Cp is equal to minus m omega square r into r cap. See, the centripetal can also be said as a force towards the center. The origin of the centripetal force can be gravitational force, tension in a string, frictional force, Coulomb force, etc. Any of these forces can act as a centripetal force. So, in the case of whirling motion of a stone which is tied to a string, the centripetal force on the particle is provided by the tensional force on the string. Now, in a circular motion in an amusement park, the centripetal force is provided by the tension in iron ropes. Here you can see this tension is provided in this iron ropes. So second one, in motion of satellite around the earth, the centripetal force is given by the earth's gravitational force on the satellites. So Newton's second law for satellite motion is F is equal to gravitational force, which is equal to mv square by r. Here r is the distance of the planet from the center of the earth, and m is the mass of the satellite, and v is the speed of the satellite. The third one, when a car is moving on a circular track, the centripetal force is given by the frictional force between the road and the tires. And then in Newton's second law, in this case, the frictional force is equal to mv square by r. Here, in this frictional force, the m is the mass of the car, and v is the speed of the car, and r is the radius of curvature of track. Here you can see another example. Even when the car moves on a curved track, the car experiences the centripetal force, which is provided by the frictional force between the surface and tire of the car. The fourth one, when the planet orbit around the sun, they experience centripetal force towards the center of the sun. Here, gravitational force of the sun acts as a centripetal force on the planet, and according to Newton's second law of motion, gravitational force of the sun on a planet is equal to mv square by r. Now let's move to the next question, which is vehicle on a leveled circular road. See, when a vehicle travels in a curved path, there must be centripetal force acting on it. This centripetal force is provided by the frictional force between the tire and surface of the road. Let us consider a vehicle of mass m moving at a speed v, in a circular track, and the radius of the track is r, which I mentioned here for your reference. Mass of the vehicle is m, and which is moving at a speed v. Radius of the circular track is r. See, there are three forces acting on the vehicle when it moves in this circular track. What are the three? Let's imagine gravitational force mg is acting downwards, normal force mg is acting upwards, and the frictional force fs acting horizontally inwards along the road. Suppose the rod is horizontal, then the normal force and gravitational forces are exactly equal and opposite. See here, the centripetal force is provided by the force of static friction, which is Fs, between the tire and the surface of the road, which acts towards the center of the circular track. So mv square by r is equal to Fs. Already I told you force of static friction is Fs. We know that static friction can increase from 0 to maximum value, that is Fs is less than or equal to mu s into mg. There are two conditions possible. One is if mv square by r is less than or equal to mu s mg, or mu s is greater than or equal to v square rg, or root of us rg is greater than or equal to v. Here you can see in this picture the moving of a mass towards a circular path. The static friction would be able to provide necessary centripetal force to bend the car on the road. So the coefficient of static friction between the tire and the surface of the road determines what maximum speed the car can have for safe turn. That's very important. While you are driving a car, when you have a turn in a circular path, it's very important to maintain your speed. Today we are going to learn or deal with some uniform circular motion and non-circular motion. Centripetal force. If a particle is in uniform circular motion, there must be centripetal acceleration towards the center of the circle. If there is acceleration, then there must be some force acting on it with respect to an inertial frame. Already I explained you about this inertial frames, and this type of force is called centripetal. Next one, banking of tracks. You might have learned about this banking of tracks in your junior classes also. In a leveled circular road, skidding mainly depends upon the coefficient of static friction, that is mu s. The coefficient of static friction depends on the nature of the surface, which has a maximum limiting value. That means the nature of the road or the track. To avoid this problem, usually outer edge of the road is slightly raised compared to the inner edge, and this is called banking of roads or tracks. This introduces an inclination, and the angle is called banking angle. Now let the surface of the road makes the angle theta with horizontal surface. Then the normal force makes the same angle theta with the vertical. If it happens when the car takes a turn, there are two forces acting on the car. One is gravitational force mg, which is towards the downward, and the normal force n perpendicular to the surface. So we can We can resolve the normal force into two components. One is n cos theta and n sin theta. The components n cos theta balances the downward gravitational force. That means the mg. The component n sin theta will provide the necessary centripetal acceleration. And by using Newton's second law, n cos theta is equal to mg, or n sin theta is equal to me square by r. By dividing the equation, we get tan theta is equal to m square divided by rg, or v is equal to rg tan theta. We take this rg here, okay. We put m by r into v. If you take the square out, then it will give you a root to the next side. See, if the speed of the car exceeds this safe speed, then it starts to skid outward by frictional force comes into effect and provides an additional centripetal force to prevent the outward skidding. Actually, the banking angle theta and radius of curvature of the road or track determines the safe speed of the car at the turning. And at the same time, if the speed of the car is little lesser than the safe speed, it starts to skid inward and frictional force comes into effect, which reduces the centripetal force to prevent the inward skidding. That means towards the inner side of the road. However, if the speed of the vehicle is sufficiently greater than the correct speed, then frictional force cannot stop the car from skidding. Thank you, students. Thank you. Now study well for the forthcoming examinations.